In this afternoon, I'm going to talk about something a bit different, which is how we can use code that is already prepared, either code that we did before or more often code from libraries that have tools that we want, and how we can incorporate that in our own code. After we see that, we'll talk a bit about namespaces, which is where the context in which each name is recognized by the interpreter, or what it refers to, and how we can import models by importing names into our own context. And then we're going to use a library for graphics, and I'll show a few examples for plotting data. In these examples, I will also try to look at fairly realistic examples, so we will have to revisit all those things: loops, parsing data, reading files, all those things that we saw before. So this will be a pattern in the remainder of this course, in which we will visit again and again the same things we saw this morning, because those are the basics, are the pieces you always have to use to glue these things together, and then look at different libraries for you to get an idea of a sample of what tools there are available. Then, depending on what you want to do, you may have to use other specific libraries that can help you, but then the pattern is always the same. You know the basics, so you can glue the things together, and then you look at the documentation of those libraries to see how to use those functions. So once you learn this pattern, it's much easier to carry on from there. So we're going to see a simple example of plotting data, how we can improve those steps that we do to all the functions that we have, and we're going to see also how we can do an animated plot with a series of images and do that automatically. So let's start with this idea of a namespace, which it's not really a dictionary, but you can imagine it as a dictionary that the interpreter keeps. So a namespace is a mapping of names that are somehow defined and what those names refer to: functions, variables, things like that. And there are different namespaces where the interpreter looks for those names, and depending on the context, it will only consider some particular namespace. The idea of having different namespaces is that we can reuse the same name in different contexts to mean different things. For example, suppose that I define this name f. This is a variable. It's a string. I store this value there. So now the interpreter knows this name and knows what it refers to. And now I call the split method to split using a comma. And I have this error because the interpreter doesn't understand what this split means. In this context, there is nothing called split. But then I say f.split. So I'm saying, look in the namespace of f and look for split there. And then he understands that it's the method split that belongs to f. So this means that f can have its method split, so it splits the data that is stored in f. But you can also use split in another string, because the namespace is different, or have a split function that does something different. And as long as the namespaces are separate, there is no confusion between the names. So this is an important part of Python, how the interpreter looks into the namespace to keep things separate. We also saw this in functions. We know that names created inside the function are separate from names outside or in other functions. And this works because the interpreter will look at these four namespaces in order. It will look at the local namespace. For instance, inside the function, it will look first for the meaning of the name in the namespace of the function. Then, for the enclosed namespace, this happens when a function generates other functions. We'll see that at the last day of the course, so let's keep that suspended for now. But then it looks at the global namespace, which is the namespace of the module, the file where you have these functions. And finally, there is the built-in namespace, which is a special namespace where you have all these built-in words like print, def, and things like that, which are part of the language itself. So it knows what those mean in any context. So if I write this source code, my script starts by putting this string, in global, in this variable 1, and then defines this function that prints the content of variable 1, creates variable 2, I am local, and prints variable 2. So when I run this, I run my function. I start by looking at the value of variable 1. So the interpreter will look in the local namespace. There is nothing called variable 1 inside this function, but then it will look at the global and find a variable 1 here. When I create a new variable inside the function, even if another function, a variable of the same name exists outside, it will be created in the namespace, in the local namespace of the function. So this variable 2 is created inside the namespace, in the namespace of this function, in the local namespace, and so when I print variable 2, it will fetch this one. This means that if I have this function and I try to print variable 2 here in the console, I will get an error. This variable 2 does not belong to the global namespace. Variable 1 does, so I have it still here, but variable 2 only belongs to the namespace of each instance of this function. Actually, once the function ends, this namespace is thrown in the garbage because the function is not running anymore. So I don't have access to variable 2 here. If I change the value of variable 1 and I run the function again, this changes what the function prints out. Because now I'm calling the function will look for variable 1 in the global namespace, and that's the same one I have here in the console, so I'm changing that variable. If I create a variable 2 in the global namespace and call the function, variable 2 inside the function did not change, because this is another namespace, and the other variable 2 inside that namespace is different. The way the interpreter decides this is that in this function I am trying to read variable 1 before declaring it here. So the interpreter cannot find variable 1 in the local namespace and then looks for it in the global namespace, finds it, and accesses its data. In this case, there is a variable 2 in the global namespace, but once I create a variable 2 here, the interpreter will create that in the local namespace. It always creates the variables in the local namespace. There is one option: I can declare the variable as global and force it to be created in the global namespace. But in any case, whether there is or is not a global variable with that name, every time you assign some value to a variable inside the function, the variable will be created in the local namespace, so it will not interfere with variables outside. So you don't need to memorize this, but just keep in mind this sort of rules. The interpreter will look in the local namespace of the function, then in the global if it doesn't find, but when you create a new variable, it will be created in the local namespace, so it doesn't interfere with other global variables. Now, we can use this also between different modules. What we need to do is to tell the interpreter that these names are in a different module, but we want to use them in our namespace too. So the global namespace is the namespace of one Python file, one module. But we can bring names from other files into this Python module. We do this with the import command. Usually you don't need to put all the imports in the beginning, but it's good practice to do so, because then you look at your module and you know what it depends on just by looking in the beginning. You actually only need to do the import before you use the name, so that when the interpreter finds that name, knows what it refers to. But it's good practice to put the imports all at the beginning. So we did, in the morning, we created this module for solving the quadratic equation that has this solve quadratic function. Let's suppose we save that in a Python file called quadratic.py, and we have that file in our folder or in the Python path. But usually, if you create your own, it's more practical to have it in the same folder. When we do this, import quadratic, this is the name of a Python file, a Python module. So now the interpreter will import that name into our global namespace, and remember that this name refers to that module. It will also run the module. So everything the module does, defines functions, constants, whatever, is executed and is associated with that name. So this module now, this name has its own namespace, like any object in Python. So now we can call the solve quadratic function from the quadratic module by indicating the namespace. So below quadratic, inside quadratic, there is this function. We want to execute it with this parameter. And the interpreter can find it because when we did import quadratic, it ran the whole module, it declared all these functions, and it knows this function belongs to that module. So this is a practical way in which you can bring into one module code from different modules, and it helps you organize your code, how you distribute the functions, and so on. In this case, we imported the module itself as an object which has all these functions and variables below it. If we try to use the function like this, it's the same problem as happened with the split method. Solve quadratic does not exist in our namespace. It only exists in the quadratic namespace in this case. So this gives us an error because the interpreter doesn't know what this means. We have to do quadratic dot solve quadratic to indicate that it's a function that belongs to that module. So if we want a specific function or class or some element of a module and not the whole module, we can do this type of import. From a Python module, a file, we can import some name that exists there. So again, the interpreter will run that module, will execute everything in the module, and then from all the defined names there, it will import directly into our namespace the names we specify here. In this case, it will work as if the solve quadratic function existed in our module. This name is now part of our global namespace, and we can use it to access that function. So now we don't need to put quadratic before and call this way. So this is typically what you do when you have a module that may have other things. Note that this function may depend on other functions from that module. That's okay, because when the function runs, it has its own namespace, and its global namespace is the namespace of the module it belongs to, and so forth. So everything works fine. But you are just importing that name into your own module. So now you can use that function as if it was part of your module, even though it's running on the other module. Okay? This we usually do when we want specific parts of the module because we want to reuse that code. This is generally the best way to do it when we want lots of different things from the module, so we just import the whole module and use it. There is an alternative which is from a module import and you put a star, an asterisk. This imports all the names from the module. I didn't put that here because that's not a good idea, because since you are importing names into your own namespace, if names are equal, then you'll have problems. When you do it like this, you know exactly which names you are importing and you are controlling that process. If you just put an asterisk, any change on the other module may cause some unwanted behavior then on your program. So try to avoid that. The best way is to do either this or import the whole module with its own name. Also, if you have a module that has a large name and you want to import that name but don't want to type that name all the time, you can use this alias. So I can import quadratic as QD, and now this is the name I call the module here. This can help to avoid collisions between names, or just to simplify typing in some cases for very widely used modules. So let's see an example of how we can do this to do plotting. How we can use this to do plotting. We have this matplotlib library, which has lots of different modules for plotting. We are only going to see a very small part of it, so if you want to see the documentation for plotting, it's good to look at the tutorials and the documentation for this library, because it has a huge number of options, a lot of things we can do. But for a very simple example, just to create one image, we can do something like this. We import the pyplot module from this library. This is one module for plotting, which has one kind of syntax. This is one of the most used here. There are others like PyLab and things, modules that look more like MATLAB and so on. So depending on what you're used to for plotting, you may choose different ones. But this is a very used one, and often it is aliased as PLT. So instead of writing this whole thing all the time, we just call it PLT and then use that as the name of the module. And now there is this function inside this module, which is plot, that we can use to create a graph and do the plot. Basically, you have to tell us the x values and the y values, and then if you do this on the console, if you have the inline, if you're using a graphical console like IPython and you have inline plotting, the plot will appear in the console. If you're not using that, it will appear on a window, a new window, but that just depends on what you're using. But the idea is that when you do this show, you show the window with the plot. And then in this case, you should have something like this, because these are the values. No, you need to have the library. If you installed Anaconda, this is a package with all these libraries. So that's why I recommended Anaconda, because all the libraries you're going to use are already included. This is a Python distribution that has all of these. If you just install Python, then probably you need this, and you need dependencies, because Matplotlib requires NumPy and SciPy and so on, and it's a bit more complicated to install if you do it by hand. That's why, yes, Anaconda is a large package. It actually comes with a lot more than you generally need for this course, but it's a lot more practical because you just install one thing and you have all of it, okay? Technically, a module is a file, or a Python file. So that's in this case, in these libraries, this may be more complex because then you have packages which are groups of files, and the whole library may have lots of packages. So I'm not sure if this is just one file or if this actually is a lot of files that call other files. But this is one module, and we are importing that name regardless of how exactly it's implemented. That. Mm-hmm. Yes, if you do this one yourself, that is one way of doing that. Because when you do import, the interpreter will look into the folder that you're working, and also in the Python path, which is a system path that is an environmental variable with the path for all the Python modules that you have installed. Another alternative is if you have your code in that other folder, and you can add that to the Python path. So you can do that in Python. You can call the system module and add to the path so it can find your module. But that's not very elegant, because then if you shift to another computer and the path is different, it won't work. Or you can actually install your module in your computer. This means that you will put it in a folder where Python has the modules, or add to the system variable, which is what happens when you install new libraries. So if you have a particularly complex problem that requires that, I can talk to you and we can look at the details. Yes, if it's just a bit of code that you use and you want to reuse, you keep in the same folder, or if you always have it on the other folder, then you can just add that relative path to your Python path. There are some simple tricks for that. If you want to do something more complex, you can actually do an installation script for your package that installs along with the other Python libraries. I don't cover that because that's usually not something you need to do unless you're actually developing this kind of package, okay? So this is a simple example of a plot. We give the x values, the y values to the plot function, and then when we call show, it creates the window with the graph. So let's see an example for plotting infection loads with tuberculosis from World Health Organization data. We have this data from the World Health Organization site. It comes in CSV, comma-separated value files. So these files have this first line with the column headers, the country, the ISO codes for the country, the region, year, population, and so on. And these include values for the estimated number of people infected with tuberculosis and the upper and lower levels of the estimate. So the higher estimate, the lower, and the average estimated level. So what we're going to use is to load the CSV file. Actually, a CSV file is not very hard to parse because it's a text file with these conventions, with the commas and the quotations for the strings and so on. So we could do it manually, like we saw the examples this morning with HTML. But now that we know how to import functions from other modules, we can actually use the CSV module, which you have installed, which already has functions to parse CSV files. So this is a lot more practical than writing the code for ourselves. And in general, for most of these kinds of standard problems, parsing HTML, XML, CSV, things like that, you often have already code done or libraries that can do this. So just if you have a specific problem like this, it's a good idea to Google for a few minutes and see what you can use that is already made. So we're going to import the CSV module, and we're going to create this function to load the data. We're going to load the data as a list of values, and what the CSV file does, the CSV module does, it has this reader function that gives us an object that can read line by line the file, the CSV file. And for each line, it automatically breaks it on the commas, it identifies the strings, and it gives us a list of values for all the values in that line. So basically, we can read the table row by row using this object. And this is what we're going to do. We're going to call the reader with the name of the CSV file. This is the file name. We open it first, so we have this file object for Python that can access the file, and we're going to give that object to the reader, and we're going to specify what is the delimiter here, the comma, what is the character used to indicate strings, and so on. Now, there are a few things here that we haven't seen before. First of all, the way you know what you put into these functions, you have to look at the documentation of each library. Because this is not standard Python, this is how each function was implemented and how each library works. So you shouldn't try to memorize all of these things. Some of these things, if you use them a lot, you'll end up memorizing them, but that's not the first approach. It's just that if you're using the library that reads comma-separated value files, you look at the documentation, see a few examples, and see how you run those functions to read your particular file. Another thing that we haven't seen before is this way of passing arguments to a function. So we saw our simple functions that we have the parameters in some order, and then we put the arguments in the same order. For instance, we have this solve quadratic function. We have the a, b, and c. We give it the values, and they are put in the parameters in the same order. But it can happen that you have a function with a large number of parameters. You can put default values on those parameters too, and then you don't need to give all those arguments to the function. You just need to give those that are not the default values. And to do that without having to write everything in the long string of values here, that will not be very informative, we have this alternative way of passing arguments to the function, which is to indicate the name of the parameter. This is actually the name inside the function, so you have to know that in this case. This is the name of the parameter. You put an equals, and then you put the value that you want to assign to it. Usually this comes with the documentation of the function. So remember that when we did help, we saw the signature of the function, which includes all the parameter names there too. So it's easy to find out what are the parameter names for the function, so you can use this and assign values by name. Typically, when you use libraries that can do a lot of things, they have functions that need to receive a lot of parameters. Usually the default values are okay, but if you need to change a few of them, the most practical thing is to tell which ones to choose. The rule here is that if you start by assigning a value to a parameter by its name, from then on, all of those assignments must be by name. Because from this point on, Python does not know the order in which you're giving the value, because now it may be any order of parameters. In the beginning, you can give the argument values by order. So this in file will go into the first parameter of the CSV reader function, which is the object of the file from which it will read the data. And then from this point onwards, you're just filling in whatever parameters you want, and it will no longer look at the order. So the rule is that once you start using this name equals something, these names must be names of the parameters of the function, and from this point onwards, all the arguments that you give must be by name and not by order. So in this case, we open a file for reading. This, by the way, the B there, this R is for reading, which is optional, because if you omit this, Python will assume that it is for reading. This is another parameter with a default value. The B means that it's binary. And this is important in some cases because when you open in Windows or in Linux, there are different combinations of characters for lines, for new lines. And depending on the operating system, there may be an internal conversion between these characters. And in some cases, for instance, for a CSV file or something like that, this may cause confusion. So if we tell it to read as binary, then it will not make any conversion and will simply supply the file as it is. But all these details, these are not things that you need to memorize, because these are things that are in the documentation of the CSV library. So when you look at the examples how to read the CSV file, it will tell you first open the file, do it in binary because Windows causes problems, and so on. Okay? So you don't need to know this from the start, you can look it up. So what we're doing here is we open the file, we give it to the reader function on the CSV module. We specify the delimiter, the quote char is this double quote, and we say that quote non-numeric on quoting. This means that things that are not numbers are considered strings, things that are numbers are considered numbers. So the reader function will automatically convert numbers into actual numbers instead of just the text strings taken from the file. So this way, as long as it's not inside quotes and it's not text, it will be converted. Now we have this CSV file object that allows us to fetch one line at a time from the CSV file. But this is still an object that we can use to read one line at a time. But we can read everything and convert that into a list using this list function. This is a basic function from Python, and what it does is it receives any object that can get the next item. So anything that is iterable, you can find the first item and the next one. So this kind of objects have those methods implemented, and the list function takes all of them and puts them all into a list. So what we're doing here is converting all of this into a list, and now we have a list with all the rows of data. Again, you don't need, this seems a bit like wizardry. I didn't invent this. This is something you look up on the library documentation, and you see the examples, and you have these examples, okay? So you don't need to invent these kinds of things. But this is just to show that using the library, we basically, in 3 lines of code, we get all the data in the CSV file, all the numbers converted to numbers, and everything organized into a list with all the rows in place. So this is quite handy for processing this kind of information. So now we can see, we do this, we put in a table the result of loading data from this CSV file, and now we print the first 3 rows from our table, and this is the result. The first row is the header here. Note that they are all strings. The second row is the first row of data, and note that these values were converted into numerical values. So the reader function did this all on its own. And then this goes on. We can print, say, for the row 100 and the 101st row, so row index 100, we can print the first 10 cells there, and we have this row here. So we can examine, we have all the data as a list of lists. Each item here is one list, and then inside that list we have the row, inside the list for each row we have the cell for that row. So now what we need to do here is extract the data that we want. So find for each country that we want the years and the infection load so that we can plot the graph. So we can do this, get the infection values for the country. What we're going to do this here is we get the complete table. This is a list with all the rows. We have to look through the table, and every time we find the country with the code that we provide, we append to this new list the data that we want for that country. And the data that we want is the year, the estimated infection load, and the upper and the lower bounds of the estimate. And these are in these columns, so we have to look up at the actual file to find the columns, but once we know which columns are the ones we care about, we can write the code. So basically this is, again, is a very simple function. We start with an empty list. We receive the table there. This table is a list of lists because each row is itself a list. So when we iterate like this for row in table, this variable row will in turn point to each of the lists corresponding to one row on the table. So if we look at the third element of row, so this is index number 0, index number 1, index number 2. This is the three-letter code for the country, and this is the one this function expects. So we look at the three-letter code for the country, and if it's the same as the code the function was supplied, then we will append to this list the values of year, average, and lower and upper bounds for the infection. And we'll put that as a tuple. So these four values we'll add to the list. And we'll do this for all rows that have the code for that country. This way we have a function that extracts from the complete table the data that we want for the country that we want. And now we have it all sorted into a single list of tuples. So we can look here at the data for Portugal. We have data for 1990, 1991, and so on, and this is just the data for Portugal because all other countries have different codes, so they were not added here. And now we have all the data that we need for plotting the graph. The thing is that this is not the right shape because we have one tuple for each year, and what we actually need is the years in one vector, and then the values in another vector, and so on. But we can easily do this by writing a simple function that we give the data like this, so a list of tuples. We say which value we want here in the index, and this function simply creates a list with the values in that index for each tuple. So it goes through all the lines in this matrix, and then creates a list with the values at the index that we want. So basically it's retrieving one column from that smaller table. For example, if we get the country infection for Portugal, we have this data here, and now we convert these tuples to a list using the index 0. The index 0 at each line is the year, so what we obtain here is a list with all the years. And then we do the same for index 1, which is the infection load, and so on, and we have these vectors with all the values. There is actually a much simpler way of doing this, which is to use this zip function, and then using this operator. This operator takes a list and converts it into a series of arguments. Each element of the list has an argument. But I'm not going to actually explain this because this would be a bit confusing. The idea is just to to tell you that there are lots of ways of doing things in Python that become a lot simpler when you know how to do them. It's easier you write less code, but there is a trade-off because you really have to learn them first. So our goal here will be to give you the basics so that you can actually do things, even if it's not very efficient, you can get things to work. And then if you need to improve things, well, that will be after the course on your own time when you want. You can keep developing these skills. Okay. But so now we're going to do this the step-by-step way. We have this function that we indicate which column we want, and it brings it all in a list. And now we write this code to get from this table and the code for the country. We're going to do the plot for the infection load. So we get the infection data for the country using that other function, and now we're going to get a list for the years, the median, the average estimated infection load, the low estimate and the high estimate, by calling successively this function to get each of the columns. And now we can do the plot by using these values here, these lists with years, the estimates. We can create a figure and then plot each of them with a different color. And here we have a new example of how to use plot. Instead of using the default values, the first example I gave, we only provided the X and the Y values, and the color the plot decided on itself. You can also use a formatting string here to indicate how to plot. So if anyone here is familiar with MATLAB, this is basically the same thing. But in any case, the example here is that we have one letter to indicate the color, K for black, R for red, G for green, and this line indicates that you want to join the points with a line. So you're drawing a line with this color. This is not something also to memorize. You just look up the documentation, see the examples, and choose the way you plot. But actually there's a lot of other parameters for plotting, like the thickness of the line, whether it's dashed or not, or something like that. There's lots of things that you can change. So plotting has a lot more detail than what I'm showing here, and depending on the kind of graph that you want to do, you just have to look at the documentation and see the options. But basically this is our plotting function. It receives the table with the data for all countries and the code of the country we want to plot. It extracts the data for that country using that get country infection function, and then it builds these lists of the years and the infection by going for that smaller table and looking at each column, and then create a figure for plotting. This way we can specify the size and the ratio of the figures. So the first is the horizontal dimension, the second is the vertical dimension on the figure size parameter. So we can have the aspect ratio of the figure, we can decide that. Then we do the three plots. We plot the three lines with three different colors. We set the title for the figure, and we show the graph. So we have this. This is what we get. We load the data. We call the function plot country with this table, with all the data and the code. Actually, this line here in the middle is not doing anything because it was part of the rest, probably a copy-paste effect. But all you need is to load the table and then call the plot country function. And this is what happened to tuberculosis infections in Portugal in these years. So we can plot this data. So this is one example of how to use libraries, in this case CSV Reader and Matplotlib, the PyPlot to do the graph, which have most of the code needed for this. We just write the small parts of code to glue things together, to select the data that we want, plot it, and so on. Now we should write documentation and, yes?
Now can we export this kind of plot to use in a PowerPoint?
You mean the images? Yes. It's a savefig. I'm going to show you an example. But you have in Matplotlib you have a function called savefig, Actually, all these plots I'm showing are images generated by the code. So you just call savefig and it saves as a JPEG or a PNG or something like that, whatever you want, and then you have the image. But I'm going to show that example too in the animation that we're going to make. So another important thing when you're writing this code that we saw this morning is to test everything properly. So this is an important part because once we decompose the problem and start implementing the several pieces of the solution, we need to make sure each piece works properly before trying to assemble everything together, because this can become arbitrarily complex. If you're going to reuse your code and your code has some defects, has some bugs, then it's going to affect everything you do with it. So it's important to be careful about testing each part of your program. So this makes everything much easier if you test systematically your programs, and not only that, but you keep a battery of tests ready so that when you change anything, you can retest it again to make sure it still works, because sometimes we introduce new errors when you make changes. One easy way of doing this, actually Python has some unit testing libraries that if you're going to use some more sophisticated development, it may pay off to look into them and to use them. But to not to spend too much time trying to learn those things now at this stage, I'm just going to talk about an easy way of incorporating your tests into the modules that you create. Every time, each module, each Python file is also on the interpreter, it's considered an object. So it has a name method, a name field there, or there is a variable called name, which is underscore underscore name and then two underscores again. This is a convention in Python. Those names that start and end with two underscore are magic names, are things that usually are at a very low level of the language, and we should not mess with them or change them or things like that. But we can read them to check what is being done with that module. So when you run a module, when the module is the main module in a program, the one you press F5 to run, for example, or the one that is executed by the interpreter, its name is called main with two underscores in the beginning and end. If the module is imported from another module, its name is the name of the module, so the name of the file without the CY extension. So this means that you can test whether or not your module is the one being executed, or if it's only being executed because it was imported by another module. And this is a good way of putting there all the tests. For example, we can do this for our module that does the plotting of the tuberculosis load. We can do at the end of the script, at the end of the source code, we can do this. If the name of the module is main, then we're going to load data from this file, print this, and do the plot for Portugal and so on. So all these tests that we've done. This means that if you run the module on, say, Spider, or if you execute it on the command line, but if this is the one being run, it will automatically run all the tests. So if you're changing something in this module, if you're writing the functions differently or adding some functionality or something like that, you can immediately test if everything is working. But if this module is imported from somewhere else, then its name will no longer be main. It will be the name of the module, and none of this will run. So once your module is ready and you have tested everything, you can now use everything that you put in that module by importing it into your own code or another script that you're doing, and it will not execute the test. So this is a practical way of keeping always a battery of tests that you can run whenever you update your module, but they don't interfere when you actually use the code by importing it into another module. Now, another thing that we should do is to document our module. The module itself can also have a docstring, exactly like function. So the docstring on a module is the string that you put in the beginning of the module. So you can write whatever you want. Typically, you describe what the module does, which functions it has, and give some examples of how to use. This can be useful not only for other people who are going to use your model, but also because after some time we tend to forget how things work, even the things that we did. So it's good to be able to do help when we import the module and then look at the documentation. So the way this works is that if you import, if this is our module, TB+, if we import TB+ and we ask for help on this module, we get the description of the module and this, what we put here basically. Okay? So the doc string, we can read it when we ask for help on the module. Exactly as it happens with, the function. So let's see an example that is a bit more complex. We're going to plot data that's actually three-dimensional data. So we have, in this case, I'm going to use life expectancy, gross domestic product, population of the country, and then look at that over the years. So we have lots of information that we want to look at the same time. So we're using an animation, and I'm basing this on the Gapminder site where you have lots of these good animations. Unfortunately, the founder died already, but this is a very great site for visualization and for data. So we're going to use these files with life expectancy, population, and gross domestic product per capita for different countries. And these are Excel files which have the name of the country in the first column. Then we have years in different columns, and then the values corresponding. Although some values are missing, not all of the values are present for all the countries. And furthermore, it's not always the same year for all the indicators. So some indicators we have some periods, others we have others. So this is not uniform, but we have all these Excel files like this. And what we want to do is this kind of animation. So this is China, Portugal, Spain, and Germany, and we are looking at gross domestic product here in a logarithmic scale, and the life expectancy here in the vertical. The size of the circle is proportional to the population. So you can see the population increasing when the circle increases, and this is going over the years starting from 1960, I think, and going up to 2000 and something. So this is what we want to do. We want to plot how, for instance, China increased first life expectancy and then GDP started increasing, and we see these three very close together here, but China closely coming near the others, quickly coming near the others in GDP and so on. So to do this, we need to generate one image for each year and then join everything together and create the animation. And that's the part we're going to automate. So we don't have to do this by hand for tens of years. We can generate all the images in one go. So first we need to think about how we're going to store data. Now I'm going to again complicate a bit here, but this is something that happens a lot when you're actually dealing with real data. You have to think about how to organize the data that you have. And the problem here is that we need to know the data for each country, and we need to know which year each value corresponds to. But this is not a simple table because there are years that are missing, different indicators start at different times, and so we cannot put everything in a very neat table. What we need then is to keep the correspondence between the year and the value, for instance, gross domestic product, and we need all that for each country. So we can create a dictionary of dictionaries. This is a dictionary that has each country as a key, and the value associated with that country code is another dictionary which has all the years and the values for some indicators. So, for instance, gross domestic product would be a dictionary of dictionaries. The first key would be the country. When we ask for some country, we get a dictionary which has year and gross domestic product pairs associated. So this is what we're going to do. We're going to read each Excel file into a dictionary of dictionaries relating country and year and value. So to do that, we're going to use this Excel read library to read the Excel file. And then for plotting, we're going to use the Matplotlib PyPlot. So we're going to do this at the beginning of our source of our module, we're going to import the two libraries, and then we'll write the code from there. Now here is the function that loads one of those Excel files into a dictionary of dictionaries. The first thing we do is to read the Excel file. This we do it by using the Excel read open workbook with the file name. So basically, the open workbook function on this library simply reads the Excel file and gives us an object that allows us to access the contents of the Excel file. One of the methods in that object is the sheet by index, which allows us to choose one of the worksheets on the Excel file and returns an object that gives us access to the data on that worksheet. So this is what we do here on the first two lines. We read the file into that object, then we pick the first worksheet because that's where the data is, and this object here, sheet, is the one which has which allows us to access the table with the data. And now this object has several fields and methods. So for instance, this nCols field gives us the number of columns that have data. So we can know how many columns in that worksheet are filled with data. And this allows us to fetch all the years for those indicators. We start with an empty list of years, and now we run from column index 1, which is actually the second column, the first one is index 0, up to the end of the columns that have data. So what we are doing when we look at the Excel file, this is column index 0, but we start with column index 1, and we go to the end of the table, as long as it has data there. And we look at the row. So we look at the cell value for row 0 and for this column. And row 0 is the first row here, and we are actually looking at the values of the years. So we are preparing a list, an ordered array of all the years that we have in this Excel sheet. This is necessary because different files from this database have different ranges of years. So we cannot assume which years they have. We have to read them from the Excel sheet. So now we have this list with all the years that are accounted for in this data file, and now we're going to create our dictionary. We start with an empty dictionary for all the countries. We read the name of the country for each of the rows, starting from the second row up to the end. Remember that the first row is 0, but the first row is only the headers and the years. We don't want that one. We're going to look at the first column, column index 0, for that row, for the name of the country. So we pick the name of the country. We start with an empty dictionary for the values for that country. And now we're going to look at all those columns that have data, and we're going to get the cell value from that row and that column. If this is different from empty, because it happens a lot that we have empty values here. If we have empty values, we don't want to add them to the dictionary because we don't have any value for that year, for that country. So if the value at that place in the Excel sheet is not empty, we will create in our year indicators dictionary, this is a new dictionary that we create here, an entry with the year, the same year that we have here. So actually we are going from the second column, index 1, to the end, but we have a list of years in which the first year is the first element of the list, which is index 0. So we need to subtract 1 from that index to align the two, because we are skipping one column, but we have a list with the years. We could do this differently by, for instance, adding a dummy value there and starting also the years on the second element of the list. Then we would not need to do this. But this is the kind of thing that it's a small detail, but you often have to think about this when you're dealing with the data, because a mistake here would, for example, misalign all the years with the data. So we'd get all the data shifted 1 year more or 1 year less, depending on how you're doing this. Okay? So you have to pay attention to these types of things when you're extracting data. So what we're going to put here on this dictionary is an entry with the year as a key, and the value in the Excel sheet as the values. So we are creating entries. For instance, these ones we don't put anything because they're empty, but here we put for 1807 we put 26.98 and so on. Now, after we do this loop for all the columns, we have in this dictionary year indicators all the values for all the years for that country. So now we check to see if this has at least a minimum number of points that we want. This was another parameter on our function because some countries may have so few data points that we don't really need to store them, we don't want to plot those. So we can add this to allow us to select what is the minimum number of data points we want. So after we look through all the columns and gather all the data for all the years, we check if this country has at least this amount of data. And we can do this by looking at the length of the dictionary. The length of the dictionary is the number of entries in the dictionary. If this length is at least as much as the minimum we desire, then we add an entry to our complete table in which the key is the name of the country and the value is the dictionary with all the values for all these years. And then when we go back in the loop, we create a new dictionary for the year indicators and we do it again for a new country. So we are adding all these dictionaries into a larger dictionary with the countries as keys. This sounds a bit complicated, but it's actually not much code, and most of the work which is parsing and processing the Excel file, that one would be really hard to do. It's already done in the library. We're just looking at the row and column exactly as if we were using the worksheet and using the coordinates of the table. So now we can test this. We import our load table function, this one, from our module, and we load this Excel file, which is the life expectancy at birth indicator, and we ask for the life expectancy in Portugal in 2001. Notice here the syntax. This LifeX is the dictionary of dictionaries with country and year. If I ask for LifeX Portugal, this returns the dictionary corresponding to Portugal. But then if I index that dictionary with 2001, then I get the value for entry 2001, which is for year 2001. Okay? And I can check this against the data to see if it's correct, see if I did not make any mistake loading the data. So this is how we can test the function. Now we're going to plot the data. We want to draw a circle for each country. The X and Y coordinates will be some indicators that we choose. The radius of the circle will be another indicator. For instance, we can use GDP, life expectancy, and population. But we can generalize this and write the function so that we could use any indicators for this. So we can try other correlations or look at other indicators. And now we're going to need to do a bit plotting that is a bit more sophisticated. We need to manipulate the plotting a bit better. So we're going to create a figure object, then obtain the axis. The axis object is the actual plotting region, so the one that controls the plotting. And we need to set up all the things, the colors and so on, and then show the image. So this is what we're going to do. To do this kind of plotting, we can call the figure function from the plotting library and store the results in a variable. Because now we have an object that allows us access to the figure. This is not necessary for simple plotting because the library remembers the figure that it made, and when you tell it to plot, it plots on that figure. But if you want some fine-tuning on the figure, it's useful to retain the object so that you can use it. So now we're going to add these axes to the figure and we specify how much of the image we are taking. So basically this is a fraction of the area of the figure that is going to be occupied by the plotting region, by the region with the axis. And then we're going to plot on the axis these values and show. This is basically the same thing, but you have more control on where the axes are on the region and how you do the plotting. So let's see how we can plot a group of countries on a figure that was already created. This function for creating the circles for the countries will receive these axis objects, so where the plotting is done, and will receive these three dictionaries. The dictionary with the values to use for the x-axis, the dictionary for the y-axis, and the dictionary for the circle size. These are the ones where we're going to put those indicators, but this way we can choose which indicators go where when we call the function. Then we have this size scale for the circle because we need to adjust the scale because the circle may be in millions or thousands of millions, or there are indicators that have very different ranges of values, so you need to scale that. And then we specify the year we want to plot and which countries we want to plot. Now, these countries need to have two types of information. We need to know the code of the country, or the name of the country to plot, and the color we want to plot it in the figure. So we're actually going to give here a list of tuples which has both the name and the color in pairs, so we can specify before calling the function which color goes for each country. So now we're going to see for each country here, we're going to get the name of the country. The name of the country will be the first element in this tuple, and this year. We're going to get the value from the dictionary in the x value, and this will be the x value for drawing our circle. The same thing for the y, and the same thing for the size. The size, I'm doing here this sort of calculation because if you want the area of the circle to be proportional to the value, you actually need the radius of the circle to be proportional to the square root of the value, and then we use this scale so that the circle does not become too large or too small in our graph. But basically it's the same thing. We're going to gather the data from each of these indicators for this country and from the year. And the reason why the country 0 is in here is because these countries are pairs of values which have the name in the first element and the color in the second one. So I know for this country what color the circle will be. And this is an example of how we can do this circle. I'm going to plot a circle at coordinates x, y. The marker will be an O because it's a circle. The fill style will be full. I'm going to paint all the circle the same color. The marker size will be this size, so the size of the circle I can control here. I put an alpha of 0.5. This is to make it semi-transparent. So alpha is opacity. If alpha is 1, it's completely opaque. If alpha is 0, then it's invisible, but you can fine-tune it so when they overlap, you can see the one that is behind. And I've set the color too. This is an example of how we can do a bit more sophisticated plotting, controlling these visual elements. And now we can plot all the countries in one image like this. So let's see how we do this on the script. We import that load table and the circle country function, this one. Now we load the three Excel files with the three indicators that we want to use: life expectancy, gross domestic product, and population. For each one, we only want countries with at least 40 data points. All those countries that don't have 40 data points will not be in the dictionary. And now we specify which countries we want to plot. This is the list that has the name of the country and the color. The colors are three values for red, green, and blue that we mix together to make the color of the country. So Portugal is green because it has 0 red, 1 green, 0 blue. Spain is yellow, which is red and green. China is red. Germany is black here. So we specify the different colors and the countries we want. And now we create our figure of 15 by 10 inches. We add these axes. They occupy almost all the figure. Remove the auto scale. Set the limits for the x and the y. And also indicate that we want a logarithmic scale on the x-axis. This is because gross domestic product varies a lot, so if we don't have a logarithmic scale, the graph becomes a bit strange. But this is just to set up the image. We set up the labels for the axes and so on. And now that we have all the plot set up, we call the function to draw the circles there. And we have a problem here that we can see when we run the code, we have an error. This is because when we look here, we are trying to find the value for this year for this country. If the value does not exist in the dictionary, we have an exception, which is this one, key error. In this case, for Germany, there was no GDP data for 1960, so our program stops because there is an error. This is also something that can happen in many cases. You are not expecting the data to behave in some way, it does, and then your program stops. The standard way of solving this in Python is to capture these exceptions. That is, we tell the interpreter that if something goes wrong there, what it should do depending on what goes wrong. So this is what we're going to do here. Instead of having the function like this, we're going to add this try except block. So inside the loop, we're going to tell the interpreter to try to do this. If there is an exception, and that exception is key error, that means that it tried to find a value in the dictionary, but it did not find it, and things went wrong, then don't just ignore it. That. We could do other things. We could output a warning, write to a log file, stop the program with a warning because it was a critical error. But in this case, what we want to do is, if we don't have data for that country, for that year, we simply don't plot the country, and it won't appear on the graph. So basically, if something goes wrong here, and if it's this sort of wrong, if something else goes wrong, we don't want it to be captured, because if something else goes wrong, we have to look into it and see what's happening. But this one, we know what it is. If there is a key error exception, we want the interpreter to ignore it. So this is what we're going to do this. We tell the interpreter to try to do this. If there is a key error exception, then just move on, pass on to the next one, and ignore it. So now we're going to write this function to draw the countries in the same image over the years. We give it all the same things, the indicators, the axis, the size, but now we give it a list of years in which to do the plot. And this function simply looks through all the years and calls the other function to plot the circle. So basically we are adding circles over circles over the years, and we can call the function like this. We create the image and we plot everything in this range from 1960 to 2012. And this is basically what we have. We have all the plots from 1960 to 2012. Since we did that exception capture, any country that lacks data in one of these years won't appear for that year. So there may be some gaps here, but our program does not stop and works for all the years. But we want to do this as an animation. There are some libraries for animation in Python, but the problem is that they only work while you're running the program. So if you want to do an animation that you can then use, say, in HTML, something like that, you have to save it as a GIF file or some kind of animation format. And the simplest way to do that is to write down all the images and then simply import them into an image editor like GIMP, for example, and then build the GIF file. If you want to automate creating the GIF file, there are modules for creating GIFs, like image to GIF or something like that, or you can use external programs. But typically, if you want to generate the plots, there are lots of good things in Python, but for image processing, it tends to be rather specialized, and usually image editors are better at doing this sort of thing. But you can also run them from the command line, and if you need to automate all of this, it's relatively easy to do. So basically, I'm going to show the example of writing all the images, and then we import it into GIMP or something and do the final processing. So this is a function to build the animation. It does everything. We load the three indicators. Now, for each year in the years that we want, and for the countries that we want, we're going to create the whole image. So we're going to create a new figure, put the year in the title. Notice here another typecasting. The year is a number, is an integer. The title has to be a string, but I can use this string function here. This function receives something that is not a string and returns the string equivalent. So you can easily glue these things together like this. Then we create the axis again, set the scale and so forth, and then we call that function to draw the circles for the countries. And after that, we save the figure with a name that is the year converted to string, and then PNG extension. And this function detects the type of image that we want from the extension and saves the graph to the image. Then we, instead of doing show, because we don't want to see this plot, we just want to save it, we do close, and we close this figure. The reason for doing this is that plotting can take a lot of memory, and if you do, say, 100 images or something like that, you'll probably go over the limit of your RAM. So it's good to, for each image you create, you throw it away after, and you recreate everything from scratch. And then I just put this print here because this can take a few, like a minute or so, and we see the progress there as it's generating the image. And after it generates the images, we have this result. Notice that Germany is missing from the beginning. That was the error that we had there. We don't have the GDP values for Germany for 1960 and so on. So it's not plotted at that time. But since we captured that exception, our program doesn't stop and just simply ignores this country and moves on. So now we have all the images, we can put them together and do the animation. So the important part here is, first of all, those basic things we saw in the morning, they're always the same. Doing the loops, the conditions, the variables, and so forth. There's a lot of confusing information here about how to do the plot, how to use the CSV reader, and so on. But this is not something that you really need to know. You have these libraries, you Google a few examples, you adapt them to your code, because this is not quite the part of programming. This is just using the code someone else already wrote. So all you need to know is which parameters you have to give and how to use it in each situation. And typically these libraries have documentation, so you can see the examples and look them all up. So the basic idea is that you learn what you can do here and how to look up this information, which libraries exist and so on. And then once you know how to read the code and you understand the basics, it's very simple to understand all these examples that you find and then incorporate them into your own code and use these libraries. This takes some work in the beginning, because if you have to think about how to write an if and how to write a for and so on, it's quite hard work to program, but all these things are always the same. So eventually these become very natural, and you just focus on adapting and doing what you need to do, and it actually becomes a lot easier than doing it by hand. So I generally don't. One of the things that happened a few years ago was that I gave up using PowerPoint and Express and so on, because it was hard to automate the slides. With HTML, I do all these slides in HTML because the images are in a folder apart, and I can automate the generation of the images. So if I look at the slides and I don't like the colors, I just run the script again and change all the images. Don't have to do it by hand. So once you start using these things more often, there's a lot of things that become easier to do by programming. Of course, it takes a bit of time to go over this initial part, but then it pays off. So suggestions for this week: you can, depending on how comfortable or uncomfortable you are with the programming part, the tutorials have, the initial ones are very detailed, and also the lecture notes, you can accompany the code I showed here. So one possible exercise is to follow those things step by step and try to do them yourself with time. You don't need to do everything in a few hours, and email me if you have any questions. So during the week, try to do some revisions here. There is also, if you're interested, the console that you're using, the IPython console or the Qt console that you can use independently from Spyder 2, they are graphic consoles. So for quick analysis where you have to plot things just to look at the data, it's often better to do it all in the console instead of writing a file or having windows popping up and so on. So you have these options in those graphical consoles. I'm not going to detail this here, but you can look at chapter 3 of the book, or just look online at the documentation on the IPython console, and you have several examples. But the idea is that you have this graphical console that you can do this sort of plotting interactively. You tell it to do the plot, you see the plot, and then you change things, and this may be good for quick data analysis. The reason why I don't invest much time here is that this tends to be useful only after you really know how to use Python. For the beginning, it's best if you write everything down on the source code, because then you save the file, and if you make mistakes, you just have to correct. You don't have to write everything down again and so on. Only after you pass that phase and you no longer make many mistakes and you already have your tools ready, and with a few lines of code you can do a lot of things, then it becomes more productive to use this sort of tools. Also, I would like you to, if you already have an idea of what you're going to be working on during this week, to email me a brief description of what your problems will be, so that for the last session I can customize a bit the lecture, focusing on what you're actually doing, instead of just giving examples that may not be very interesting for you. Because especially for those who don't want to do the evaluation and wish to focus on their actual work, it's much better that I can help you with those specific problems. We can be much faster, move much faster that way. Okay?